just to kind of see what you remember and make sure we're using the same terminology here. RT, or total resistance, what's it going to be for this? 6 ohms, very good. Total current? 2 amps, very good. 12 volts over 6 ohms is 2 amps. I2, that's the current through resistor 2. What's that going to be? 2 amps. Series circuit, current has to be the same everywhere, right? Power, total power produced. 24 watts. It is 2 amps and 12 volts. So 12 times 2 or 2 times 12 is 24 watts. P2 is the power lost or dissipated over resistor 2. Well, the current there is 2 amps. What is the voltage drop? Well, 2 amps times 4 ohms is 8 volts lost drop there. So that's going to be 2 amps times 8 volts would be 16 watts. Is the power dissipated or the power used across resistor 2. Does that all make sense? Yeah. Okay. Well, it is time for our first quiz. So, our next step is to talk about ratios. What a ratio is a comparison between two numbers. So we might have number of students in this class compared to number of students in my next class. There's 4 in here, and there's 12 in my next class. Now I could write it like that as a fraction, 4 over 12. I could write it with a colon, 4 to 12, like this. Or I could write it as 4 to 12 with the word 2 in there. I will typically write them as a fraction because there are a lot of things I can do with a ratio that are similar to what I would do with a fraction. One of them is to reduce it. Both 4 and 12 can be divided by 4, so that reduces to 1/3. One thing I want to note is there are 2 types of fractions. I have the 4 to 12 over here. What I'm doing here is I'm comparing 2 pieces. If I consider you guys as a separate class to the other class, I'm comparing, call you guys part A to part B. But if I considered all you students together as 1, I could have written that instead of 4 to 12, I could write it as 4 out of 16. It's the same ratio, describing the same relationship, but a different way of putting it. 16 is now, instead of just part A, it's the total of both of you together, the 4 plus 12. Kind of like if I had, let's say I have 8 ceramic and 12 of the old glass insulators. I could do a ratio here of 8 ceramic to 12 glass. That'd be 8 to 12. Or I could do 8 out of, what would the total be? 20 total. So when it's written out like this, it's very clear. This is 8 to 12. It's comparing one part to another. 8 out of 20 is saying it's comparing 8 out of a whole. So the 20, when it says out of, that 20 includes that 8. When it's written as a fraction like this, it's a little less clear which one it means. Or even if it's just written with the colon like this one, it's a little less clear which one it actually stands for. So you have to make sure you understand what those ratios are. You guys don't do a whole lot with solutions, but they talk about dilutions with solutions. Let's say you have a concentrated formula that you have to dilute down. You have to perform a 1 in 5 dilution. What that is saying is that 1 in 5 ratio, the 1 represents the concentrated liquid or whatever it is. The 5 is the total solution. So it's not 1 part concentrate to 5 parts water. It's 1 part concentrate in 5 total parts. If I wanted to do the concentrate to water, it would still be 1 part concentrate to how many parts water? 4. Very good. If 1 out of the 5 is concentrate, the other 4 out of the 5 is water. I might look at these tables here, and let's do a length to width ratio. The length of these tables are 6-foot tables, that's 72 inches. The width, they're 1.5 feet, so it's 18 inches. I can reduce that as well. The inches cancel out. Both 72 and 18 can be divided by 18. Gives me a 4-to-1 ratio. Now here's one big difference between our ratios and a fraction. If this were a fraction, I'd just write that as a 4. As a ratio, I have to make sure I leave that as a comparison between two numbers, 4-to-1. You'll also notice that the units disappeared. The inches disappeared. You might be wondering, well, what units go on there? And the answer is it doesn't matter. For every 4 units of length, there's 1 unit of width. Or for every 1 unit of width, there's 4 units of length, however you want to look at it. Whether that's 1 centimeter of width for 4 centimeters of length, or 1 foot of width for 4 feet of length, or whatever unit you use, as long as they're both the same, the ratio will still work out. You'll notice in all the ratios I've created, the units have been the same, inches to inches. This was milliliters to milliliters, or parts to parts. Up here, it was students to students, insulators to insulators. In a ratio, the units or the labels on the two numbers we're comparing must be the same. So if I have 2 feet to 18 inches, that is not a ratio the way it's written because they're different units. Now, fortunately, I can change that. 2 feet can become 24 inches to 18 inches, and now they're the same units. Now I can reduce. Inches will cancel out. Both of those, 24 and 18, can be divided by 6 to give me a 4-to-3 ratio. Now, here again is another difference between a ratio and fraction. If that were a fraction, I'd make it a mixed number, 1 1/3. As a ratio, 1 1/3 makes no sense. It is 4-to-3. What if I'm comparing two numbers that can't be given the same label? Like, let's say we'll send you on a road trip, and you're going to drive 365 miles in 7 hours. There is no way I can turn miles into hours or hours into miles. This is what we call a rate. And that is the first big difference between a rate and a ratio. A ratio always compares two things with the same label. A rate compares two things with different labels. The second big difference, while a rate can be, or a ratio can be expressed as a unit ratio, like this is a unit ratio, the denominator is 1. I could have turned this into a unit ratio, but it would have been awkward. We said the 1 1/3 would have been 1 1/3 to 1. You have to leave it as a comparison of two numbers. That would be a unit ratio. More often than not, we leave a ratio like this. It's 4-to-3 or 2-to-5 or whatever. A rate is almost always expressed as a unit rate. So that means we divide out the denominator, at least the number of the denominator. So this is a 7, we're going to divide by 7. 7 hours divided by 7 is 1 hour. 365 miles divided by 7 is what, 52.142857143 approximately miles. He's going to double check me. Sorry, go ahead. So that's a unit rate. The denominator is 1. Now I'd round that off. I'm just showing off a little bit there. Probably to 52.14. And more often than not, we would hide the fraction in the units. So it might be like miles per hour, like that. Am I right? Okay. So that fraction gets hidden in miles per hour in the units. In fact, sometimes we hide the appearance of the fraction altogether. Let's say that on that trip you get 26 mpg. What's mpg stand for? Miles per gallon. When you see 26 mpg, you have to think this, 26 miles per over 1 gallon. because this is the form you need it in to do calculations with it later. Excuse me. Rates are all around us. We've talked about miles per hour, miles per gallon. An important one for you guys might be dollars per hour. Your wage is a rate. Again, that's $18 over 1 hour is technically what that is. You might have usage rates. You know, gigabytes per hour would be a usage rate and stuff like that, or bytes per second, kilobytes per second, stuff like that is your transmission rates and things like that. Ratios are also everywhere. We might look at well, I'm going to draw some pictures and see how if you guys can understand my artwork. There is a reason why I'm a math teacher, not an artist, by the way. Just clarifying that one up front. Any guesses? Years, good. A gear ratio is the number of teeth in the driven gear over the number of teeth in the driving gear. So this gear has 14 teeth and this one has 7. How do I know which one is which? Well, we need some more information. Let's say that I draw, pretend that's a little electric motor. If I separate the gears, which one stops? The 7. That's the driven gear. It is being forced to turn by the other gear. It is being driven by the other gear. So the driving gear is the one that's connected to the power, or more closely connected to the power. That's the 14. So, of course, that can be reduced to 1 to 2, 1.5, 1 to 2 ratio. Technically, as a ratio, we wouldn't call it 1/2. We would have to say 1 to 2. We also have pulley ratios. Pulleys don't have teeth, so what we use are the diameters. Now, the reason we count teeth on the gears is because for the gears to mesh, the teeth have to be exactly the same distance apart. So we can measure the size of the gear just by counting the teeth. Measuring the diameter of a gear is tough because where on the tooth do you measure it? Do you measure it on the outside of the teeth, the inside of the teeth, part way? Technically, it's a pitch diameter you got to measure. It's actually part way out the tooth, so it's tough to measure. So counting the teeth is the easy way to go. For pulleys, you measure the width where the pulley rides. That's down inside the V of the pulley is where you have to measure it to, where the belt rides. So let's say this is 4 inches and 10 inches. And let's give you motor again. Which one's going to go on top, the 4 or 10? The 10. If I cut the belt, that's the pulley that stops right there. That's the driven pulley. So the 4 goes on bottom. That's going to reduce. Inches cancel out. It reduces to 5 to 2. You might look at, I'll do one more mechanical one here before we move on. We're really going to stretch my artwork now. Any guesses? Pistons. We're going to look at compression ratio. Compression ratio is the expanded volume over the compressed volume. So the expanded volume is bottom dead center, the largest volume above the cylinder, above the top of the piston in the cylinder that you can get. Let's say that's 480 cubic centimeters. That's going to go on top over here. Compressed volumes at top dead center and the pistons at the top, and there's the smallest volume possible. Let's say that is 60 cubic centimeters. So the cubic centimeters cancel out. 480 and 60 both divide by 60. Give me an 8-to-1. A compression ratio typically does get reduced to a unit ratio, but we still have to leave it as 8-to-1. You can't just say 8 or 7.5 or something like that. You still have to say 7.5-to-1 or 8-to-1 or whatever. On construction, you guys might run into a roof. Let's say this is 24 feet across and 6 feet high. A lot of people don't realize there's a difference between a slope and a pitch. A slope is a rise over run. A pitch is height over span. The 24 is the span. The 6 would be either the height or the run, or the height or the rise. The run, half the span. You got it, 12 feet. So the slope is 6 over 12. Rise over run. Slope is always given over 12. It's actually inches per foot, so it's inches per 12 inches. Pitch, height over span, would be 6 over 24. That does get reduced down to a 1/4 pitch. A lot of people use the term pitch instead of slope. They call it a 6/12 pitch or a 4/12 pitch. It's not, it's a slope. Pitch dates back to when you actually did old rafters systems, ridge beams, where the pitch describes how high the ridge beam goes above the wall. So it's a little bit different approach to it. Let's look at some other applications. You might look at a specific analysis. Let's do everyday life. You're going to run into a debt to income ratio. If you ever want to take out a loan, they're going to look at a debt to income ratio. Depending on who you're working with. Debt to income ratio a lot of times is a 1-to-3 is the max they let you do. So let's say you guys get out of here. What are you guys expecting to make per hour? No idea? We'll be generous with you. 16? Okay, so we'll give you 16 bucks an hour. 16 bucks an hour times 40 hours a week times 4.3 weeks in a month. So let's just do $27.50 a month is what you're going to, just a guess at what you're going to make. Okay? So $27.50 will be your income. Debt payments only include payments on loans, credit cards, things that must be paid every month, and it's things that would appear on your credit report. So it does not include food, gas, utilities, even though utilities sometimes do appear on your report. So let's look at car loan. Anybody have a car loan? Yeah, how much a month do you pay, if you don't mind sharing? $250. Okay, that works. Yeah, we don't have to be too exact. Credit cards. We'll give you a lowball number of $100 a month. Student loan. $260. Let's round it up to 300 just to keep it easier on us. But yeah, that $200 to $300 a month is usually typical for student loan. So right there we have, what, $650 total for debt payments. That's not including any personal loans. So let's say you want to go buy a house. Okay. A 1-to-3 ratio can also be thought of as a 1/3. 1/3 of your income can be debt. So 1/3 of $2,750 is about $915. What that means, you subtract your $650. So $915 would be about a little bit less than your 1-to-3. Technically like $916.67 or something like that would be 1-to-3. So anyway, this leaves you with about $265 a month that you could put onto a house payment. Not going to find much of a house for that payment. A lot of students come out of here and they want to buy that new truck. They got the money for it. They end up with a $500 a month car payment or truck payment, whatever. Well, now there's like $15 a month left over for a house. So even once you get your student loans paid off, right, $300 a month is a little big for the student loans, but I did that on purpose. Even once you get that student loan paid off, you only got like $315, $320 left to make a house payment. So you get that big car payment, you're putting yourself in a real bind if you ever want to buy a house. Let's look at some specific electronic applications. Transformer ratios. Transformer ratios, there's a couple of them. You guys gone over transformers yet? A little bit. You know, transformers are used to either reduce or increase voltage. Yep, exactly. Step up or step down. So we're going N1 and N2 is the number. N1 is the number of turns in the primary coil. We'll just go primary and secondary. NP and NS. So this is your voltage going in. This is your voltage coming out. So your transformer ratio is usually the ratio of the coils in the secondary coil to the number of turns in the primary coil. So if there are fewer turns in the secondary, this is a step down. If there's more turns in the secondary, it'll be a step up. There are other ratios that are associated with this. Voltage. Another way of doing it is your ratio of voltage in to voltage out, or voltage out to voltage in. That's going to go on, again, off of the number of turns in your coils. Another ratio you end up with is a bridge ratio. I'm going to throw out a typical Wheatstone bridge here just because that's the easiest one for me to draw. A Wheatstone bridge is anywhere you have a load connected between branches of a parallel circuit. So here, this is a parallel circuit right here. Your bridge would be something connected across here. The reason you use bridge circuits is it's easier to control the voltage, the balance of voltages in a bridge circuit. Because most of your resistors have like a 10 or a 20% tolerance. Controlling your voltage tightly using strictly just different resistances to dissipate or control your voltage used is very iffy. It's very sloppy. A bridge, if you use three set resistors, and then a potentiometer, a variable resistor, you can very, very precisely control voltage with it. So this is going to be the set side here. We'll call this R1 and R2. This over here is going to be RW and R variable. So the ratio here in the bridge is just going to be R1 to R2 is our bridge ratio. For this to be a balanced bridge, by balanced means there's zero current, 0 amps flowing through here. The ratio of RW to RV has to be the same as, oops, I put an R1 ratio. Has to be the same as the ratio of R1 to R2. If that's the case, no current will flow either way. If RW is larger, if this ratio is larger, RW over RV is bigger, current's going to flow that way. If our W over RV is smaller, current's going to flow the other way. So it's also a way of, you can have current flowing either direction. Anybody ever play with a model train set when you were a kid? No? You got the little transformer, you turn it one way, the train goes forward, turn it the other way, the train goes backwards. That is a bridge circuit by a potentiometer, a variable resistor, causing the current to flow one direction or the other. Okay, I am going to give you guys some packets to work in here. In one packet, I'm just going to call it the PPM packet. It's going to be Unit 28. And the other one is going to be, I should call it the electronics packet for now. It's going to be page 252, 1 through 12 that I want you to work on. So any questions?